Okay, so what we saw from the last example is that if I have a curve C defined by the vector function r of t, okay, each point here can be described by the vector function r evaluated at particular t. So for example, this point here is going to be evaluated by r of, let's say, t naught. Okay, so in order to find the tangent line to this curve at that particular point, what did we do? We found the derivative of r of t, and that gives us um, the vector r prime of t. And what is special about this vector r prime of t is that it is parallel, right? It is parallel to the tangent line. Okay, but now recall that as a vector, right, if we multiply it by any constant, any positive constant, is going to keep the direction. And if we multiply by any negative constant, it's just going to have the negative direction, right? But it's still going to be parallel to the tangent line. So a natural question that arises is that what would be the most, let's say, basic tangent vector, right? Because all of those, so derivative of r of t multiplied by any constant is going to be parallel to the tangent line. So which one is going to be, let's say, the building block, the basic one? Well, we have a name for it, and it's called the unit tangent vector. Okay, so everything is in the name. It's a tangent vector. That means it's the derivative of the vector function with magnitude 1, a unit tangent vector. Okay, so for any vector, how are we going to for any given vector v, how are we going to find a vector in the same direction with a magnitude 1? Well, simply we have to do is divide the vector by its magnitude, okay? And that exactly is the definition of the unit tangent vector called t, unit tangent vector. So it's a vector with magnitude 1 is equal to r prime of t, so the derivative of the vector over the magnitude of r prime of t. So what do we have? I have a vector in the direction of the derivative divided by its length, which gives us what? Which gives us a unit vector. So this formula here, as we're going to see in the next few sections, is very important. This idea of the unit tangent vector will keep on revisiting it over and over in the next 2 weeks. Okay, so let's do an easy example. Example 1, find the unit tangent vector of the vector function 6 cosine of 3t 3 sine of 4t. Okay, again, look at the definition of the unit tangent vector. First, I have to find the derivative of the vector function. So r prime of t is simply derivative of 6 is 0. Derivative of cosine of 3t is negative 3 sine of 3t. Derivative of sine of 4t is 4 times cosine of 4t times 3, that's 12 cosine of 4t. Okay, so we have found the derivative of the vector. Now we have to find the magnitude of the derivative of the vector. Okay, so the magnitude of the derivative of the vector is equal to the square root of what? Of sum of the squares of all of the components, so that's 0 squared, which is 0, plus negative 3 sine of 3t squared plus 12 cosine of 4t squared, which is equal to square root of 9 sine squared of 3t plus 144 cosine squared of 4t. Okay? And finally, the unit tangent vector is going to be what? R prime of t, 0, -3 sine of 3t, 12 cosine of 4t, over the magnitude of the derivative of the vector. That's square root of 9 sine squared of 3t plus 144 cosine squared of 4t. Okay, so this is the general formula for the unit tangent vector for this curve. And now you can, of course, evaluate this at any point. You can see here the first component is a constant, the second component is a cosine, and the third component is sine. Cosine and sine are defined on R, so I can evaluate this. I can evaluate the unit tangent vector for any point as long as the denominator is not 0. The denominator will not be 0, so let's say pi over 2 is going to be equal to, the first component is 0. Sine of 3 pi over 2 is -1 times -3 is 3. Cosine of 2 pi is 1, so 12. Let me just make sure that I got that right. 3 pi over 2 -1 times 3 is 3, and cosine of 2 pi is 1 times 12 is 12, over, and now we have sine of 3 pi over 2, so that's square root of 9 times sine of 3 pi over 2 is -1, squared is 1, so 9 times 1, plus cosine of 2 pi is 1 plus 144, which is equal to 0, 3 over square root of 1, how much is this, 53, and 12 over square root of 153. So this is the unit tangent vector at this particular point. Okay, now let me give you another example. Example 2. If the question says find the unit tangent vector right away at pi over 2, you can save time without finding t of t, the unit tangent vector at any point, right? So you'll see what I mean. Find the unit tangent vector evaluated at pi over 2 where r of t is equal to sine of t, 2t, and 3 cosine of 3t. Okay, again, first of all, you have to find the derivative of the vector function, that's cosine of t, to -9 sine of 3t. Okay, and now instead of finding the magnitude of r prime of t, first I'm going to find how much is r prime of pi over 2. That's cosine of pi over 2, which is 0. This is a constant, stays constant. And sine of 3 pi over 2, that's -1 times 9 is 9. Okay? And now I will find the magnitude of this one, r prime of pi over 2, so that will save me a lot of time in finding dealing with the square roots, right? Pi over 2, that's square root of 0 squared plus 4 plus 81, which is square root of 85. Finally, t pi over 2 is equal to r prime of pi over 2 over the magnitude r prime of pi over 2 is equal to 0 to 9 over square root of 85. So make a difference between the question being find the unit tangent vector at pi over 2 and find the unit tangent vector. Okay, if you're just asked to find the unit tangent vector for any t, of course you have to find the the derivative of the vector function here, then find the magnitude of the vector function for any t, and this would be your answer, right? Just following the formula above. But there is a faster way to do this problem if the question says find t of pi over 2, right? The unit tangent vector at pi over 2, the unit tangent vector at pi over 2 is r prime at pi over 2 divided by the magnitude of r prime at pi over 2, and we save time by just finding the first derivative and then right away evaluating it at the given point. Next thing that we will do is are the properties of the derivative of vector valued functions, or so derivative of a constant times the vector function is the constant times the derivative of the vector function. The derivative of sum or difference of vector function is the sum or difference of the derivatives of vector functions. So far we were just following the standard properties of derivatives of functions, and now the product rule. Here we have to be a little bit careful. Why? Because when we deal with vectors, we have three types of products. First, a function times a vector function follows the standard product rule. Then what happens when I have dot product between two vectors? Again, is the same, is the dot product of is the derivative of r dot product v plus r derivative of dot product derivative of v. And the last thing happens when I have the cross product. Okay, so the derivative of cross product of r and v is r prime cross product v plus r cross product v prime. Okay, and at the end we have, you can recognize this as the chain rule. So let's do an example here. It says show that r dot product r prime cross product r double prime, and now derivative of this whole product is equal to r dot product r prime cross product the third derivative of the vector function. So we have to show this equality. Okay, so let's start from the beginning. R dot product r prime cross product r double prime prime. Okay, by this rule right here, that's r prime dot product r prime cross product r double prime. So r prime dot product this plus r dot product r prime cross product r double prime prime. Okay, so here at this point I want to stop for a bit and discuss what is going to be the first product right here. What happens when I have r prime cross product r double prime? When I have r prime cross product r double prime, this will result in a vector orthogonal to both r prime and r double prime, right? So if I have here r prime and r double prime, the cross product is going to be a vector r prime cross product r double prime that is orthogonal to both of this, right? So this cross product is orthogonal to r prime and r double prime. We've talked about this. But then dot product between two orthogonal vectors is how much? Is 0, right? So if u is orthogonal to v, then u dot product v is 0, right? So this whole product is simply 0. Again, I'm going to repeat. The cross product between two vectors results in a vector orthogonal to both of those. So this product here is orthogonal to r prime. So this vector that's orthogonal to r prime dot product r prime by this rule right here is simply 0. Okay, so we are done with the first component and we can simply concentrate on the second one right here. Okay, for the second one, now I have to find the derivative of the cross product. Okay, so let's do that step by step. This is r dot product, the derivative of the first multiplicand, derivative of r prime is r double prime, cross product r double prime, plus r prime cross product r, the derivative of r double prime is the third derivative of r. Now again, I want to remind you that u cross product u is also equal to 0. The cross product between the vector and itself is equal to 0, which means that this part here is 0, and this results in finally the result that we were looking for, r dot product r prime cross product r, the third derivative of the vector. We will do another example like this, and that says that the derivative of, if the length of the give me a second here, if the length of the vector function is a constant, then the derivative is orthogonal, the derivative of the vector is orthogonal to the vector for any t. Okay, so let's prove that. So what did we say? If we know that the length of the product is just r dot product r, and by assumption this is equal to a constant. Let's find the derivative on both sides. ddt of r dot product r is equal to the derivative of a constant, and this is just 0. Here I have r prime dot product r plus r dot product r prime, which results in 2 times r. These are the same, right? And the commutative law works here. So 2 times r dot product r prime is equal to 0, or simply r dot product r prime is equal to 0 if I divide this one by 2, right? But from here, obviously, this implies that r is orthogonal to r prime. So one obvious case where r of t, the magnitude of r of t is a constant, is the sphere. Let's say in our case this is a unit sphere, so that means a sphere with radius 1. And what does this say? That if I have this point right here and this is described by r of t, okay, then the vector, let's say that this curve, this is the direction of this curve, then this is going to be r prime of t, and these two vectors are orthogonal. Okay, similarly, if I take this point right here and this is r of t, well, this is my son, everybody say hi to him, and then I take, then this is going to be the vector r prime of t, and these are going to be orthogonal, right? Let's just keep in mind that the derivative of the vector function preserves the direction of the curve. Okay, as you can see, this is the direction, so the derivative goes in the same direction. Okay, this picture should be a little bit more precise, but I hope that you understand what I'm trying to say. Okay, so one more time, if the magnitude of the curve is a constant, then at any point the vector and its derivative are orthogonal. And we finish this section by introducing integrals of vector valued functions. Again, similarly with derivatives, as you might expect, if I have a vector function r of t with components f, g, and h, then the definite integral of r of t from a to b is just the definite integral of each of the components. Okay? So let's do an example. I have the integral from 0 to pi over 4 of the vector function sine of 2ti plus tangent of tj plus e to the power of 2tk, which can be written as integral from 0 to pi over 4 of sine of 2t tangent of t e to the power negative 2t dt, which is just the vector of the integral from 0 to pi over 4 sine of 2t integral from 0 to pi over 4 tangent of t and integral from 0 to pi over 4 of e to the power negative 2t, and of course here I forgot dt everywhere, sorry about that, dt, and just evaluate these integrals. The integral of sine of 2t is going to be how much? It's negative cosine of 2t over 2, evaluated from 0 to pi over 4. Integral of tangent of t is ln, sorry about that, ln of cosine of t, if I didn't make any mistake, with negative in front, from 0 to pi over 4. And the last one, the integral of e to the power negative 2t is negative e to the power negative 2t over 2. Evaluated from 0 to pi over 4. Okay, and then we just evaluate these. This is going to be negative 1/2 cosine of pi over 2 is 0 minus cosine of 0 is 1, negative ln of pi over 4, sorry, cosine of pi over 4 is square root of 2 over 2, minus ln of cosine of 0 is 1, ln of 1 is 0, minus 1/2 e to the power negative pi over 2 minus e to the power 0 is 1. And we can simplify this finally. This is going to be 1/2 negative ln of square root of 2 over 2. Of course, this can be rewritten as ln of 2 over square root of 2. And this is going to be 1/2 1 minus e to the power of negative pi over 2. Okay? So the idea here is that the definite integral of the vector function with components f, g, and t is just the vector with components integral of f, integral of g, and integral of h. And of course, if this is an indefinite integral, then we would have the same vector, just with indefinite integral of f, indefinite integral of g, and indefinite integral of h, plus a constant where that constant is going to be also a vector. Okay, now you can go to section 13 point, you can go to the section of 13.2 and finish the problems. There are a lot of problems here that you can do. Let me just make sure that I have those. 13.2. Okay. So you can do in order to find the unit tangent vector, you can do problems 17 to 22. Properties of derivatives. functions 47 to 57, and then integrals 35 to 40. Thank you very much.